Okay, we're going to find arc length, and I guess let me. I've made a statement here. The Radian measure formula for theta equal S over R. Remember, pardon me. Remember, S represents the length of the arc. That's the measurement along the circle itself, divided by R, and R is the radius. This can be used to find the measure of an arc along a circle. So let me draw a diagram so that we can begin to talk about what this is. And so hold on just a second. Okay, I've got my circle drawn, and we have a circle that's of radius r, and we have this angle theta that I've labeled there, angle theta, and of course it's a positive angle because we are going in a counterclockwise direction, aren't we? And then what I'm doing is I'm looking at the distance along the circle from the initial point of the angle, the side of the angle, to the terminal side of the angle. So I'm looking at that length, that distance along the circle, and that's called the arc length. That's called theta. Now above, remember that the formula theta is equal to S over R is how we decided what the measure of the angle is in radians. We took the distance S and divided by R to find out how many radiuses are in that distance, and that gave us the radian measure. Well, we could actually go backwards. We could kind of go backwards or change that a little bit. If we multiplied both sides of that equation by R, we'd have S alone on the right side, wouldn't we? And it would be R times theta on the left side. And so that's actually what we want to do. We want to multiply both sides by R, and then we want to write it in this way. Okay? So the things to remember is that this S is the length of the arc length. And of course, this radius, this R, is the radius of the circle that we're talking about. And this theta is the angle of the subtended, the angle of the central, the angle of the measure of the central angle. I apologize over and over. But it's important to remember that this is in radians. See, because this was the formula we used to calculate radian measure. So that angle has to be in radians. Okay, well, let's keep that in mind. So, let's look at a specific case, okay? Here's our problem. Here's our problem. Let me write it out. Okay, so our problem states this. We have a circle that has a radius of 4 inches, and we're to find the length of the arc intercepted by a central angle of 240 degrees. It seems like there's a lot of extra language there. We just mean along that circle, inside that circle, we have the center, the vertex of our angle at the center of the circle. That's what we mean by central angle. And we're going to measure off an angle of 240 degrees. And where the terminal side intersects the circle, we're going to measure the length of the arc from the initial side of the angle to the terminal side of the angle. It's basically like I've shown in the diagram. So in this case, our R is 4 inches, okay, and our theta is 240 inches. 240 degrees. Now, the biggest mistake here, we're working on this solution, okay? We want to do the solution now. We're going to use the formula we have above. That formula is arc length. That's what we're trying to find. We want to know the length of that arc. Arc length is R times theta. But, here's the big deal. But theta is given in degrees. not radians. And we have to have radians to use the formula. Oh, I didn't state that very well, did I? To use the formula, we must have theta. Theta must be in degrees. Must be in radians. And so that's the problem that we run into right away. So we need to convert. Okay? Convert 240 degrees into radians, and then we can use the formula. And then the formula applies. Okay. So that's the first thing we've got to do. Well, 240 degrees, okay, 240 degrees times a conversion factor. We need the degrees to go out, and we need radians to appear. And so we use the relationship, we know pi radians and 180 degrees are the same, so the degrees will go out, and we'll have 240 over pi radians. 240 pi over 180 radians. Well, when we simplify 240 over 180, we get 4 pi over 3. Let's look at it this way. 60 goes into 244 times, 60 goes into 183 times, so that's 4 over 3, and we have a pi in the numerator. So 4 pi over 3 radians. Okay. Now, for us to continue then, now we're prepared to use the formula, aren't we? S is equal to R times theta. So in this case, our R is 4 inches, and our theta is 4 pi over 3 radians. Actually, radians are non-unitized. Radians are really a real number only, and that's why it's sometimes it's all right to leave, because it's really a measure of an arc, isn't it? It's all right to leave, if you will, no units at all. I've said that earlier. When we don't see units, we understand it's radians, and that's why we might not see units. But as we use the formula, we're thinking that we've got 4 inches times a non-unit number of 4 pi over 3, which represents a radian measure. Anyway, that would calculate then to 16 pi over 3, and that's not too pleasing to us. And of course, that's in inches, isn't it? Okay, that's in inches. That's not too pleasing to us because we don't really know how much that is. And so we would get out our calculator now and do that calculation, and I'd anticipate it would be a little more than 16. Since pi is about 3.14, we have 16 times 3.14 over 3, so that's 16 times a little more than 1, isn't it? And in fact, when we use our calculator and round to the second decimal place, we'd get 16.76 inches. Okay, remember this is in inches. So the length of that arc, if we have a 4-inch radius, that arc that 240 degrees gives us is going to be a little more than almost 17 inches, 16 3/4 inches roughly, isn't it? Well, the thing to come away from this is that to use the formula, we've got to know the formula, but to use the formula, our angle has to be in radians. So don't ever forget that when you're dealing with a problem, that we make sure that we get our angle into radians. We're going to look at an application problem here and find the distance between 2 cities on Earth that are, one is directly north of the other. But first we have to understand what latitude is a little bit. So the latitude of a location L on the Earth is the angle that is formed by a ray drawn from the center of the Earth to the equator, and then also a ray drawn from the center of the Earth to that location L. So if I was trying to illustrate this with a little miniature Earth, okay, Okay, and so you've got to kind of imagine what I'm doing here. This is the North Pole, which South Pole is below, and of course this is a sphere. I don't have a very good circle, do I? This is a sphere, so remember longitudes, we can talk about that at another time, go like this, don't they? Longitudes go like this. Okay, but we're talking about latitudes, and latitudes go like this, more or less, okay? That's what latitudes do. So suppose we have some location on the Earth, then the latitude, we're in the center of the Earth now, inside, okay, we're in the center of the Earth, and we draw a ray from the center of the Earth to the equator, because right there's the equator. Remember the equator is on the outside, of course, the Earth's surface, and then we draw a ray from the center of the Earth to that particular location. And so we measure that angle. When we measure that angle, that's called the latitude of that location, L. So here's our problem. Glasgow, Montana is due north of Albuquerque, New Mexico. Oops. As I read this, I see I missed a letter. Find the distance between Glasgow, which is at 48 degrees 9 minutes north latitude, and Albuquerque, which is at 35 degrees 5 minutes north latitude. Now the north part means that we're measuring from the equator north, and so we could have south latitude. That'd be we measure from the equator south. But here they're both north of the equator, so those are the latitudes of measurement. Now, as a little diagram, let me kind of get you, let's look at a cross-section of the Earth, okay? And we're really looking at a cross-section here. And we know the radius of the Earth, okay? Now what we've got is for instance, Albuquerque, let's look over at this side. Albuquerque is about right here. And boy, that's a tiny writing, isn't it? Albuquerque. Okay, and now remember it's north, so I'm looking at this. I'm looking at a cross section that goes through both of those cities. Okay, and so I'm looking at that from the side. But if I looked at it head on, then one would be north of the other. And so this is where Glasgow is. Okay. Of course, that's Glasgow, Montana. Let's be careful of that. Now, what I need to know is the angle between these. See, I'm looking for, this is the distance that I want to find, okay, that arc length. And to use that arc length, I need to know r and theta. And so that's how I'm going to do this calculation. Now, r I'm given. See, the radius of the Earth I'm given. So r I'm given, and theta is what I need to find. That's this angle. I wasn't told that, and I've got to make sure that it's also in radian measure. But if I have those two pieces, then I can find that distance between the two cities. So the job first is to find the angle theta any way I can. And so remember, here's the idea when we look at it this way, is that, I'm going to kind of throw this down to the side. Let's look at this as going to the equator, and this is going to, if you will, Albuquerque, and this is going to Glasgow, okay? Now the information I've got, those aren't great deals. I have this angle. See, this angle is told to us to be 35 degrees and 5 minutes. And I'm also told this angle, see, that's the latitude, remember that's for Glasgow, and that angle, I'm told, is 48 degrees and 9 minutes. And so the angle theta is the difference between those two. See, the angle, this is what I'm wanting, so I take the big angle and subtract the smaller angle from it. This is the angle theta that I want. And so theta is actually 48 degrees, 9 minutes, subtract 35 degrees, 5 minutes. Well, 48 degrees subtract 35 degrees is what, 13 degrees? And 9 minutes subtract 5 minutes is 4 minutes. So that's the first thing. Now I know that my angle between the two cities there that I'm interested in is 13 degrees and 4 minutes. Well, I've got several problems. First, I need to put that all in degrees, and then I need to convert it to radians. So to convert this into decimal degrees, I take 13 degrees and 4 minutes, and I do what? Remember, I'm going to say, oh, that's 13 degrees plus 4 minutes, but when I convert 4 minutes into degrees, I need to take, 1 minute is 1/60th of a degree, isn't it? So I've got to take those 4 minutes and multiply each by a 1/60th of a degree, and when I do that, I get 4/60ths and so on, and that's going to be approximately 13, and that decimal will be 0.0667 degrees. I've got several decimal points there, okay? Now I need to convert that. Now I've got it all in degrees and completely decimal degrees, but I need to convert that. So in radians is what I'm trying to get, okay? Up there it was degrees. So I take my degree measure, okay, degree measure, and I need to multiply so that degrees go out and radians come in. And so that means I need pi over 180, doesn't it? Now when I do that, I'm going to get radian measure because the degrees go out. And I use my calculator, and I'm sure that you can do that as well as I can, and I approximate that to 0.228 radians. Okay, so now I've got my angle between the two cities listed in radians rather than degrees, and now I'm ready to go. So the arc length that I'm looking for, S, being r times theta, and theta is in radians, okay, theta is in radians. Well, r is the 3,960 miles, and the radians, of course, is 0.228. And when I do a calculation on that, I get approximately 903 miles. Remember, the 3960 is in miles, and truthfully, radians are not, don't have units really associated with them. So that's the reason it comes out in miles. Pretty cool, huh? Actually, a little historical note here. Let me kind of just sketch out going backwards. How do we know that the center, the radius of the Earth is about 3,960 degrees? No one's drilled to the center, and no one's drilled all the way through and measured the diameter and taken it by half, so how do we know that? Well, historically, this is actually what happened. It's kind of the reverse of this problem. Take two cities or take two locations. Take two locations where one is directly north of the other, okay? Take two locations where one is directly north of the other and measure the distance between those. So this time we're measuring the arc length. We're measuring the arc length. Now, once we know that arc length, okay, we could anticipate what the angle is going to be. So, we would do it in a way, we would measure in a way, and this is a little bit steep, but we would measure in a way where we know the, if you will, the latitudes. And so we know the angle between the two cities as well. And so if we know the angle between the two cities and the distance between the two cities, then the only unknown would be the radius of the Earth, wouldn't it? Okay? And so we can use that information to calculate the radius, and that's a real rough sketch of what took place. I'm leaving a lot of details out, obviously, and there's still some questions, but the idea how it was ever determined what the radius of the Earth is, and likewise we can use that to calculate the circumference of the Earth. Okay, next we want to talk about the areas of sectors of a circle, and we'll begin that on the next page. So here, as I mentioned, here we want to discuss finding the area of a sector. And I guess first we need to know what a sector is. When we're talking about a sector, we're talking about a sector based on a circle. And so a sector, if you will, is like a piece of pie. If the circle is, if the whole pie is the circle, okay, so if the whole pie is the circle, then a sector would be like taking a slice of pie. So this region is called a sector, okay? Now, we want to know how we can calculate the area of that sector. So here's what we're going to do. So we're interested in A, which we're going to call the area of that sector or that piece of pie. And let's assume now the angle, and I've kind of messed it up here. Let's assume that we're calling the angle, okay, the angle is theta, and it's the angle of that sector. And let's assume that the radius is r here, okay, radius is r. So the area of the sector is what we're interested in. Now here's what we're going to do. We're going to compare that to the area of the circle, okay? And this is simply it's just really a simple idea. Let's compare, I mean, for instance, if we had an angle that was pi over 2, which would be 90 degrees, that would be 1/4 of the pie, wouldn't it? And so we can imagine that the area of that slice of pie, this huge slice of pie, the area of that huge slice of pie would be the same then as 1/4, the area of that slice would be 1/4 the area of the whole circle. Or on the other hand, if we had a slice of pie that is, and I'm going to say it in degrees, but let's say 30 degrees, or let's say 60 degrees. Say 60 degrees. Now, 60 degrees is pi over 3 radians, but let's say 60 degrees because we understand that. Well, if we had a slice of pie that came out as 60 degrees, well, that's actually 1/6 of the whole pie, isn't it? And so to know the area of that sector, we would just find 1/6, if you will, of the area of the whole pie. The relationship would be 1/6, that area would be the same thing as 1/6 the area of the whole pie. Now, I'm not saying that well, but here's what we want to do, okay? What we want to do is look at the area of the sector that we're interested in, A, okay? Now, the fraction of that piece of pie to the entire area of the pie, of the circle. Well, how do we calculate the area of the circle? Pi times r squared. So the A is the area of the slice, and the pi r squared is the area of the entire circle. Okay, so that relationship, that fractional amount ought to be the same, okay, ought to be the same as the angle relationship, theta, to the angle if we went all the way around, which would be the circumference. And circumference we calculate as 2 pi times r, don't we? So for instance, if we had 1/4 of the way around, we would be comparing that angle to the 1/4 to the whole way around. Anyway, the relationship between the area of our sector and the area of the whole pie or circle would be the same relationship or ratio of the angle of our sector to the angle of the whole circle, which would be the circumference, 2 pi r. Okay, so we take this and we multiply both sides by pi r squared. So you could get A alone. That's what we're interested in. And we do that, we'll see that what happens here is the pi's are going to cancel, and we'll have r squared over r, Okay, and we'll have a 2 in the denominator, so we write it this way, 1/2. That's the 1 over 2 that's in the denominator. R squared over R is just R, and of course theta is our angle. But remember, we've got to do these things in terms of radians. That's the only way we can do this relationship. Okay, so theta is in radians. So this is how we calculate the area of a sector. Pretty easy to do. Let's see if I can come up with a problem. Okay, we're to this problem. We're to find the area of the sector of a circle of radius 5 feet formed by an angle of 60 degrees. So it's just really a rough sketch. That's all I'm doing here, and it's not necessary even for this. So we've got a big circle. Radius is 5 feet. Okay, and now let's look at this sector. Okay, 60 degrees. If this is my initial side here, and my terminal side would be something like this. And so we're looking at the area of this sector and remembering that this radius is 5 feet. Now, to use, remember once again, this is something to be careful of. To use A is equal to 1/2 times R theta, theta must be in radians. And we don't have it in radians here, do we? So our first job, like a while ago, is to convert 60 degrees into radians. So we need a conversion factor. Oh, okay. Then that means we've got to have degrees down here, 180 degrees, and pi radians are the same. And we see, of course, 60 over 180 is 1 over 3, so this is pi over 3 radians. Now we're ready to use our formula. So we get A is equal to 1/2 times our radius, whoops, Well, I apologize. That's just what ran into my mind when I was getting ready to use the formula. I apologize. I made a mistake way up here because I measured circumference. I compared circumference to an angle measure, and that was the mistake I made here. Remember, theta is the angle, not the arc length. So we need to compare that to an angle, not an arc length. 2 pi r is a circumference or an arc length. So the angle of one revolution is just 2 pi, isn't it, of one revolution. And so we don't have, when we come over here, we don't have the r that's in the denominator. We only have the r squared that's in the numerator. And so I wrote down my formula wrong up there. It's 1/2 r squared times theta in radians. And of course here it would be 1/2 r squared. So we take the radius and square it, okay, and then multiply it by the angle measured in radians. And of course the only thing we have, the only units we have is that the radius is in feet. So we're going to have 5 feet squared, that's in square feet then, and that would give us the result that we need. We expect area to be in square units. So what we get here then, of course, after I made that awful mistake, you'll see when we square 5, we get 25. And so we'll end up with a 25 in the numerator times a pi in the numerator. And in the denominator, we have a 2, and from that 1/2, and a 3 from that pi over 3, 6. So that's the exact amount of square feet, okay? But we would now use our calculator to approximate that, and when we do, we'd get about 13.09. It said to answer to round to 2 decimal places, 13.09 square feet. Okay. Sorry for that mistake. I got in a hurry. Well, that's all I think I need to say about area of the sector. I'm sure you can go with that and get quite a bit done.